Good morning, everyone. So, in the last section, we discussed section 24, where we mainly talked about the normal form and Sturm separation theorem. Today, we are going to talk about Sturm comparison theorem. But before that, let's talk about theorem 4, which says that yx is a non-trivial solution of y double dash plus h of x y is equal to 0, where h of x is greater than 0 on a closed interval ab. Then y of x has at most finite number of zeros on this closed interval, which makes sense. So if I consider this example, y double dash plus y is equal to 0, then for this example you know the solution. So c1 cos x plus c2 sin x, and if you consider any finite interval, you can see that the zeros of cos x or sin x are finite only over that interval, because here h of x is greater than 0. Yes, this is very important theorem which says let y and z be a non-trivial solution of y double dash plus q of x y is equal to 0, z double dash plus r of x z is equal to 0, where q and r are positive functions such that q is greater than r. Then y of x vanishes at least once between two successive zeros of z of x. Let's try to understand what it is saying. So first consider an example. So here q of x is 4, which is greater than 1, which is r of x. So it is saying y of x vanishes. Y of x is any non-trivial solution of equation 1. So let's say sine 2x, and z of x, so y of x, let's consider, and z of x is sin x. So it is saying y of x vanishes at least once between two successive zeros of zx. So consider the two successive zeros of zx, so 0 and pi, because sine 0 is 0 and sine pi is 0. So it vanishes at least once. So if you take x is equal to pi by 2, then sine 2x is equal to 0. Yes, this is what it is saying, but it has many more interesting meanings. So from the Sturm comparison theorem, we can conclude the first point is, if y of x has finitely many zeros, then can you say something about the zeros of z of x? So y of x vanishes at least once between successive zeros of z of x. So let's say these are the successive zeros of z of x. Now y of x is vanishing finitely. Let's say here it is vanishing yp1, here it is vanishing 3 times yp2 or y2, y3, y4 and so on. But since it vanishes at least once between two successive zeros of z of x, and y of x is has finite zeros, it means that z of x must have finite zeros. It cannot have infinite. On the other hand, if z of x has infinite zeros, then what can you say about y of x? So z of x is infinite zeros. So these are z1, z2 and infinite zeros. Now between every two successive zeros there is at least one zero, and there are infinite intervals. So between every interval there must be at least one zero of y of x. It means yx has infinite number of zeros. But if yx has infinite number of zeros, you cannot say anything about z of x. It may be finite, infinite, think over it. And similarly the other case. So two important case to remember is, if y of x has finite zeros, then z of x has finite zeros. If zx has infinite, then y of x has finite. For better understanding, let's do a question. So the question says that if y of x is a non-trivial solution of y double dash plus h of x y is equal to 0, then using Sturm comparison theorem, show the two things. One is y of x is infinite number of zeros if h is greater than k by x square for some k greater than 1 by 4. So for the Sturm comparison theorem, the first step is I need one more theorem, one more equation in Z. So the first equation is y double dash plus h of x y is equal to 0. And let's say I wrote the other equation because I have this relation h is greater than k by x square. If I take it as q of x and this as r of x, then this helps me to write down the another equation. This is Z. So this is my equation 1, this is my equation 2. Yes. Now see this result. Z of x has infinite many zeros, then y of x is infinite many zeros. It means if Z of x has infinite zeros, then y of x has infinite zeros using or from Sturm comparison theorem. So from Sturm comparison theorem, yes. So it means I need to find the zeros of equation 2, how many zeros it has, and also under the condition k is greater than 1 by 4. So first see how do we find the zeros. So to find the zeros, let me change the color. So to find the zeros, we need to solve it. To solve it, recall that it is Euler equidimensional equation. So z dash plus k by x square z is equal to 0 is same as x square z double dash plus kz is equal to 0. Yes. So for the Euler equidimensional equation, recall that here p is 1, p is 0 and q is k. So d2y by dz square plus p minus 1 dy by dz plus qy is equal to 0. So auxiliary equation would be m square, p minus 1 is minus 1 plus k is equal to 0. That gives me m is equal to 1 plus minus under root 1 minus 4k by 2. Yes. Now the values of the m depends on 1 minus 4k. There could be distinct roots, there could be real roots. So if I consider the case 1 minus 4k is greater than equal to 0, which is same as k is less than 1 by 4. Yes. So in that case we will get real roots. So real roots are of the form c1. I have z of x as c1 e raised to the power log, I am just calling the roots as m1 m2. So log m1x or m1 log x, sorry, e raised to the power m, because it was m1 z is log x, something like this, plus c2 e raised to the power m2 log x, which is c1 x raised to the power m1 plus c2 x raised to the power m2. Now clearly it is visible that z of x has finite zeros. Yes, this is case 1. If you consider the case 2, finite zeros because x mainly vanishes when x is equal to 0 or in some rare cases. If I take 1 minus 4k is less than 0, which is k is greater than 1 by 4, then you will get e raised to the power ax. So e raised to the power 1 by 2 log x, which is root x, and then you will get sine cosine function. So actually you will get imaginary roots. I am not interested in the final solution, we just want to see what kind of the roots we are getting. Now imaginary roots, sine cosine, they have infinite zeros, implies z of x has infinite zeros. I also consider the case 1 by 4 k is equal to 0 here, because in case of the equal roots also you will get finitely many zeros. So when k is greater than 1 by 4, then equation 1, so 4, so now we can write 4k is greater than 1 by 4, zx has infinite zeros, and then using Sturm comparison theorem, it says that if zx has infinite number of zeros, so then using Sturm comparison theorem, y of x has infinite zeros. Yes, so using Sturm comparison theorem, we managed to prove y of x is infinite number of zeros. The second case says that y of x has finite zeros. So if you recall here, then the first case helps us to find that if yx has finitely zeros, then zx has finitely zero. Now this y and z is simply a notation. What we need to remember here is that y of x means the non-trivial solution of equation 1, z of x means non-trivial solution of equation 2. Yes, so if I have to show that z of x has finite zeros, I have to show that equation 2 has finite zeros, provided equation 1 has finite zeros. So I need to choose equation 1 whose zeros are finite. So I need to choose equation 1 whose zeros are finite. Yes, so I will take the same equation which we have discussed, because for that equation we have already discussed. So if I take the equation z double dash plus k by x square z is equal to 0 as equation 1, because I am looking for an equation whose zeros are finite, so that I can show that the equation for which I have to prove the zeros are finite can be proved, and I should take it as equation 2. So equation 2 is y plus h of x as zeros. Yes, now we can only use Sturm comparison theorem if this q of x is greater than r of x. Q of x belongs to equation 1. So for Sturm comparison theorem, k by x square must be greater than h of x. Yes, and for finite zeros of z of x, k should be less than 1 by 4. This we have discussed. K is less than equal to 1 by 4. So you can also say less than equal to 1 by 4. Yes, so now h of x is less than k by x square, which is less than equal to 1 by 4. So implies h of x, I replace k by 1 by 4, is less than 1 by 4x square. So it means that when h of x is less than 1 by 4x square, z of x has finite zeros, and from Sturm comparison theorem, y of x has finite zeros. Yes, so very interesting result. Yes, I use the Sturm comparison theorem to show the finite zeros as well as infinite zeros. I am not covering more questions right now, but we will cover them in the next class based on this Sturm comparison theorem. First, try to understand what has happened and try to clearly understand the result of this Sturm comparison theorem. Thank you very much.